Hi everyone, my name is Muhammad SHAHRIL bin Omar FAROOK and my matrix number is 2411100969. So today, we are from group G07 and we want to present about our case study and the title is Modeling Gas Thermodynamic States and Jet Flame Behavior of High Pressure Hydrogen Cylinder in Fire Scenarios. In this video, I will briefly explain about problem statement, objective and also scope of this study. The problem statement: high pressure hydrogen cylinders are commonly used in energy storage and also vehicle application. When exposed to fire, the internal gas temperature and pressure increase rapidly, which this may cause TPRD activation or cylinder rupture. Before TPRD activation, the gas undergoes isochoric heating where pressure rises continuously. However, current safety approach lack a first principle thermodynamic model to accurately predict the transient temperature, pressure and time to TPRD activation, leading to uncertainty in hazard assessment. After TPRD activation, hydrogen is released at high pressure, forming high velocity jets that may reach choked flow condition and produce long jet flames. At present, mass flow rate and flame length predictions are uncertain, limiting optimization of TPRD outlet size and also safety distance. Okay, now we move to the objective. The objective of this study has two main objectives. First, to develop and validate a first principle isochoric heating model using energy balance and also a real gas equation of state to predict temperature, pressure and also the time to TPRD activation. The second is to model post TPRD venting as transient isentropic real gas flow in order to determine the mass flow rate, flow regime, jet flow length and to recommend and optimize TPRD outlet diameter. The scope of this study focus on hydrogen stored in type 3 composite cylinder under localized and fully engulfing fire condition. So, before TPRD activation, the cylinder is modeled as sealed rigid vessel using an isochoric heating with approach of van der Waals equation of state. After activation, hydrogen release is modeled as transient isentropic flow, including choke and subsonic regimes. Model validation is performed using experimental fire and blowdown data from the literature, and the main output are temperature, pressure, time and mass flow rate and also jet flame length. That's all from me. Thank you.
Hi, my name is SYAMIMI ZULKEPLI and my matrix number is 2411100988. Today I will be explaining about the literature review. So this literature review focuses on the behavior of the high pressure hydrogen cylinders when they are exposed to a fire. This topic is important because hydrogen is increasingly used in energy systems and transportations where the fire safety is a major concern. So when a hydrogen cylinder is exposed to a fire, it heats up very quickly. As a result, the internal temperature and pressure increase. This can lead to the activation of the thermal pressure relief device or TPRD, or in extreme cases, cylinder rupture. Early research mainly studied what happens after the TPRD opens. These studies focus on hydrogen jet flames, measuring flame length, mass flow rate and heat radiation. While this information is useful, this study did not look at the heating process before venting, so they could not predict when the TPRD would activate. Later experiment study improved this understanding by testing a real hydrogen cylinders in fire conditions. This experiment measured internal pressure rise, wall temperature, TPRD activation time and flame length. However, the results were limited to a specific cases and did not provide a general model that could be applied to a different cylinder sizes or fire condition. The study also addresses this gap by introducing a complete modeling approach The model covers both stages, the closed heating phase before venting and the venting and jet flame phase after the TPRD opens. Before venting, the model predict pressure, temperature, and the time of TPRD activation. After venting, it predict hydrogen, mass flow rate, and jet flame length. The model was validated using a full-scale fire test data and shown good agreement with experimental results. Overall, this work provides a useful tool for improving hydrogen cylinder safety, better TPRD design, and more accurate fire risk assessment. Thank you.
Hi, my name is AIMI BINTI JAAFAR and my metric numbers is 241112752. Today I'm going to present about research method. This study used a two-part research method to analyze the behavior of a Type 3 hydrogen cylinder exposed to fire, aligned with the study objectives. The first part examines the sealed heating stage before TPRD activation, while the second part analyzes gas venting and jet flame behavior after release. The modeling is based on first principles thermodynamics and is validated using published fire test experimental data. The first method focuses on the heating phase before the TPRD activates. During this stage, the cylinder is treated as a sealed system with constant volume, also known as an isochoric process. Heat from the fire increases the internal gas temperature, and this is calculated using an energy balance approach. Because hydrogen is stored at a very high pressure, the van der Waals real gas equation is used instead of the ideal gas law to improve accuracy. From this model, we can predict how temperature and pressure change with time and determine the exact moment when the TPRD activates. The predicted results are then compared with experimental fire test data, showing good agreement and validating the method. The second method begins once the TPRD opens and hydrogen starts venting from the cylinder. This release is assumed to be an isentropic process, which is appropriate for rapid gas expansion. Using real gas flow relations, the mass flow rate, exit velocity, and flow regime are calculated, including whether the flow becomes choked. Flame length correlations from previous studies are then applied to predict the hydrogen jet flame length during blowdown. Different TPRD outlet sizes are analyzed to identify a design that allows safe pressure relief while minimizing flame hazard. The predict mass flow rates and flame lengths are validated against experimental jet fire data, confirming the reliability of this method.
Hello, my name Muhammad ZAKWAN bin ADZIM. My metric number 241110975. Today in my section, I will explain about the data analysis and interpretation using first principles thermodynamic modeling. So the main thermodynamic problem in this study is understanding how a high pressure hydrogen cylinder behave when exposed to fire. We focus on how temperature, pressure and gas flow rate and jet flame lengths change before and after the pressure relief device or TPRD opens. So before the TPRD open, hydrogen is trapped inside the cylinder, so the volume remain constant. Heat from the fire increase the gas temperature and pressure. Using the first law of thermodynamics, this process is modeled as constant volume or isochoric heating, because hydrogen at high pressure does not behave like an ideal gas. A real gas equation is used. The model shows that pressure rise until it reach the safety limit, which agrees with experimental result. So next, after the TPRD open, hydrogen begin to leak out through a small opening. This leakage is modeled using isentropic flow equation. So this equation predict how the mass, pressure and temperature inside the cylinder decrease over time. The predicted blowdown behavior match well with experimental data. And finally, after leakage, the leaking hydrogen form a high-speed jet flame. The flame length depend on the gas velocity and exit condition. Using the Bradley correlation, the predicted flame length match the experimental observation. Overall, the result show that first principle thermodynamic can accurately predict hydrogen cylinder behavior and safety performance during fire exposure. And in summary, the first principle thermodynamics was used to model the behavior of a high pressure hydrogen cylinder in a fire. The analysis successfully predict pressurized before TPRD activation, gas leakage after venting, and jet flame formation. So that's all from me from my section, and thank you.
Everyone, my name is Ahmad Dashami HAMDI. My laboratory is 24110903. Alright, today I'm the present about the result. Consider it is one conflict issue from the jet camp. The issue one is ethical and safety risk. That means a higher cost may lead a lower capital region to use cheaper and less storage. And the second issue is economic barrier. Transition from the fossil fuel to hydrogen require high pressure storage. However, the safe option is expensive due to specialized material, creating a mechanism to rapid adoption. And the second and the second presentation is conclusion. That means the conclusion from the objective relate with the objective is successful model gas release, identify the transition between choke and subsonic flow. The second, accurately computed mass flow rate and the jet flame light. Integrate the flow in dynamic data to determine the ideal TPRD outlet parameter. And the last, balance the two need for rapid pressure relief with the goal of minimize flame impingement risk. That's all from me. Thank you.